Okay, hi everyone. So this is question 4 to 6, okay, on our set 2. And then after that, the final video will be question 7 and 8. All right, let's go straight to question 4. So we have a few man-made satellites, okay, from various countries. Okay, and so what is meant by a geostationary satellite? So a geostationary satellite is a satellite that orbits on the geostationary Earth orbit, I think. Yeah. Okay, so it's a satellite. Oh, sorry. It's a satellite that orbits on the. Sorry, I didn't have enough space, so I just want to write there GEO lah. Okay, that orbits on the geostationary Earth orbit. Now, two characteristics of the geostationary satellite. So this is very normal. The orbital period is 24 hours, is the standard one. Okay, orbital period is 24 hours is one. Okay, another one is always on the same geographical position. Okay, on the Earth is another one. Okay, or it also says it orbits the Earth in the same as the rotation of the Earth, right? So the orbital direction is the same as the direction of the Earth's what is putaran? Rotation, yes. Okay, Earth's rotation. Okay, so any two of these three, okay, we'll give you this one. So these are very factual questions. All right. Geostationary satellite of mass 1,200 kilograms is placed at 4.23, etc., etc., etc. Calculate the linear speed. So from the previous question, you know that the linear speed is V equals to Gm over R square root lah. And then don't forget that the R, since it is placed 4.23 times 10 to the power 7 from the center of the Earth. So we don't have to take the radius of the Earth into consideration. Okay, so this, remember that the down here will be just 4.23 times 10 to the power 7. G is given here, M is given here, so really not a problem. Okay, so once you calculate this, you will get about 3.07 times 10 to the power 3 meters per second. Okay, yeah, so I'm not going to waste time with the calculation, but just to let you know that when you have to read the question properly. So like in the previous question, number 3, you have to take into consideration the radius of the Earth, because R, generally, the R is always taken from the center of the Earth, not from the Earth's surface. Okay, so that's a very important thing to remember when you're doing calculation in this chapter. Okay, is that R actually always from the center of the Earth, or center to center. Okay, all right. The next one is the Earth's gravitational pull on the satellite. Now, this is a sort of a trick question. Okay, the Earth's gravitational pull is not really the gravitational force, okay, but more on the centripetal force. Okay, so they are asking you to calculate the centripetal force, but not really the gravitational force. So I would use F equals to mv squared over R, which is the formula for centripetal force. And since you have the mass of the satellite, okay, remember this is a small m, so it's 1,200 times, then you get the answer of the linear speed, 3.07 times 10 to the power 3 over the same R, 4.23 times 10 to the power 7. You should get about 267.37 newtons. Okay, and I think that's the very important thing about this. Okay, although in actual fact, if you think about it, the Earth's gravitational pull on the satellite now is the gravitational force can also be considered the gravitational force between one another. You can actually also use F equals to Gm1 m2 over R squared. Okay, the only problem is compared to the mass of the Earth, the mass of the satellite is really very small and almost insignificant. Okay, so that's probably a reason why you can use this one. Okay, because you're talking about the gravitational pull between both, which should be the same lah. Okay, if you follow Newton's third law. Okay, but if you use this formula, at least I calculated and I got about 267.05 newtons. Okay, yeah, okay, 0.05 newtons. About the same lah. Okay, but I would feel that generally the Earth's gravitational pull on the satellite should be the centripetal force, because we know that for an object orbiting around the Earth, okay, the centripetal force is always towards the Earth lah. Okay, so that's why I would use the centripetal force formula first. But I feel that if you use the gravitational force formula, because you saw the word gravitational pull, I don't think it will be a very big issue lah. Okay, since the values are almost the same anyway. Okay, what happens to the satellite if the speed is lower than the orbital speed? So if the linear speed is lower than the orbital speed, the most important thing, obviously, it will fall. Okay, it will fall into a lower orbit. Okay, this is first. Yeah, I know everybody likes to be very dramatic. Oh, fall onto the Earth. Now, first, it has to fall into a lower orbit and see if it can sustain that movement. If it can't, okay, it will enter the Earth's atmosphere. Okay, and burn because of friction. Okay, and heat. So I think the second point is a little bit more familiar to everybody, especially if you watch like rocket movies. You know that if the satellite cannot sustain the orbit, okay, it will fall into it. No, it will crash into the Earth lah. Okay, but I want to draw your attention to this first line, because I feel that this is a very important line that needs to be said simply because it is a 2-mark question. Okay, if you just say enter the Earth's atmosphere and burn because of friction and heat, I think it only allows you to have 1 mark. Okay, because it doesn't tell you why it enters into the Earth's atmosphere. Okay, because it is already on orbit. So the linear speed is lower, it has to fall into a lower orbit first. Okay, I say or go into a decreasing orbit. So I think that's a very important point that I feel that you should mention lah. Okay, as you're talking about this. All right, same chapter again, but different question. Okay, diagram 4.1 shows two bodies, P and Q, acting on one another. Okay, and we have both of different masses lah. Okay, obviously both of different masses. So the first question will be state Newton's universal law of gravitation. This is a very long answer, so I just going to give you a shortcut lah. It's directly proportional to the product of the two masses and inversely proportional to the square of the distance between the two masses. Okay, or from center to center lah. Okay, but Newton's universal law of gravitation is one of those laws where there are two things that are involved, and you have to mention both in order to get 1 mark. Okay, so it's very long lah. Okay, but if you remember it, then good for you. All right, based on diagram 4.1, let's calculate the weight. Since this is a pretty easy one, 8 and 20 kg. Yeah, so this will be 8 times 9.81, and this will be 20 times 9.81, which will give you about 78.48 newtons, and then the other one will be 196.2 newtons. Okay, this one, I think if you calculate it correctly, it shouldn't be a very big problem lah. Okay, now calculate the force between P and Q. Okay, so this is where we're using Newton's universal law of gravitation. So F equals to G m1 m2 over r squared. Okay, since G is a constant, 6.67 times 10 negative 11. M is given 8 and then 20. And then of course, the distance between them is, if you take a look, the distance is 175 centimeter. Okay, so you need to change it to meter. So it's about 1.75, and then the whole thing will be squared. So you get, after you calculate this, you get about 3.48 times 10 negative 9 newton. So the attractive force between the two is about 3.5 times 10 to the power negative 9. That's 0 point, and then 8 zeros, and then 348. Okay, so question is, are they attracted to one another? Okay, in reality, of course, they are not. Okay, why? Because the gravitational force although existent, okay, it does exist, okay, the gravitational force is too small. Because look, the force is 3.48 times 10 to the power negative 9. But the individual weights are 78 Newton and 196 Newton. How can 3.48 times 10 to the power of negative 9 ever fight with the weight of 78 Newtons? Don't even need to talk about the 196, talk about the 78 Newtons. Okay, it's so small. It is there, but it is very small. Okay, so it is very small, and then of course, if you go into further calculation, we can consider it negligible. Okay, can totally ignore the value. Okay, but that would be the reason. Okay, because the values are too small compared to their individual weights. Okay, all right, once again, we see a metal ball and then a string. At this point, if you answered a lot of gravitational questions, you know that this is probably a very popular, a very popular calculation question, which is the centripetal force. Again, the centripetal force manifests itself in many different forms. Just now was gravitational pull on the earth. Now is a tension on the string. Okay, so if it's this direction, you know that you're actually asking you to calculate the centripetal force. So you have F equals to mv squared over r. M is 0.075, okay, from the question, because it's 75 grams. Okay, and then of course, the linear speed is 1.8, then you squared. The distance between these two is 0.8 meters. So thankfully, they've already given us the value in meters. So you get about 0.304 newtons. Okay, one mark here and one mark here. Okay, so I mean, if you follow the previous video and you're looking at these two questions, you kind of know that, okay, centripetal force quite important, okay, at least where we are right now. Okay, diagram 4 shows a moving ice cream truck. Okay, 4.1, and then 4.2 shows the pattern of the wave by the two speakers, two loudspeakers. Okay, so this one, when you hear loud, soft, loud, soft, loud, soft, you kind of know that the wave phenomena that we're talking about is interference lah. Okay, anything with alternating, alternating light, loud, soft, or bright, dark is interference lah. Okay, just a few notes to take note of. Number one, the speakers were placed 0.8 meters apart. Okay, which is this. This is 0.8. Okay, and then of course the frequency is 600 hertz. The two kids walked down at 3.2 meters in parallel in front of the meters. They heard the loud sound. So I don't know. Oh, okay. 3.2 meters in parallel in front of the speakers. They heard loud and soft sounds alternatively. So it could be that this whole thing is 3.2 meters. At least that's what I understand from the question. Okay, so, hold on. Oh, sorry, my bad. No, sorry, my bad. This from here to here is 3.2 meters. Okay, so when we're talking about interference, one of the most famous formulas is the interference formula, okay, Young's formula. The wavelength equals to AX over D. Okay, and it's very important to visualize the formula rather than remember what is the formula about. Okay, because the explanation for what is A, what is X, what is D is so long that it throws people off when they try to remember the formula. So you visualize it. Okay, A is this. The distance between the two speakers, this is A. Okay, whether it is two speakers or two deepers or two light sources, the A is always the same. Okay, always the distance between the two coherent waves. That's the actual technical term. Okay, then from the speaker to the listener is the big D. Okay, yes, I know I said that. It's a big, it's the D lah. It's the big letter D. Now, of course, everybody knows the wavelength. That's very standard. Okay, and then finally, what is the X? The X is the distance between either two consecutive loud sounds, okay, or two consecutive soft sounds. Okay, that's it. That's all the X actually is. So I would suggest, especially if you have a hard time remembering what the letters mean, when you look at the formula, visualize how the formula is in terms of interference. Okay, this is A, this is D, this is X. Okay, and of course, the most important thing is remember the X is a consecutive loud and the next loud lah. Okay, not the distance between one loud and one soft. No, it's one loud to the next loud, or one soft to the next soft. Okay, because it should be sekata, it should be equal in length. Okay, so what is the meaning of two coherent sources? It's very standard, this one. Okay, two coherent sources are waves that are in phase. And a lot of people like to stop here because, of course, the most important thing is they are in phase lah. But I always like to, push you to add a bit more. So besides the fact that they are in phase, you should also mention at least two things that they are the same lah. Okay, so they are in phase, okay, with the same frequency, okay, and wavelength. Okay, so this of course is a non-negotiable word lah. You must mention the words in phase because that's really literally, almost literally what coherent means. Okay, they move together, okay, at the same time. It's not like one up, one down, like chasing one after another. It's not like that lah. Okay, so that one is out of phase. Out of phase means they're not in sync with one another. Okay, so waves that are in phase or in sync are what we call two coherent sources. But we don't say in sync. Okay, we just, I guess, well, Gen Z language, okay, could be easier to understand. Okay, the frequency of the audio signal generator is increased. So what happens to the distance between the two consecutive loud sounds? Okay, so it's a very common question in interference. They will ask you to look at the formula. Formula is lambda equals to AX over D. Okay, and they will ask you to explain it in terms of the this one. So two consecutive loud sounds is the X. So the question is, if I increase the F, okay, what happens to the X? Now, if you remember from electromagnetic waves, or not really electromagnetic waves, but if you know the relationship between frequency and wavelength, you know that when the frequency increase, the wavelength will decrease. Okay, and so when the wavelength decreases, if you look at the formula, you notice that the wavelength is actually directly proportional to the X, simply because they are on the same line. Okay, so what happens to the distance between the consecutive loud sounds? It will decrease. Okay, remember the question, what happens, will only have three possible answers, either increase, decrease, or unchanged. But in this case, since the wavelength is decreasing because the frequency is increasing, so the distance between the consecutive loud sounds will decrease. Okay, and so that's the first mark. Second mark is, why does it decrease? Because when the frequency increases, okay, the wavelength decreases. Okay, and then of course you have to mention the relationship between the two lah. Wavelength is, oh sorry, this is paper 2, so you can't say directly proportional. So the smaller, okay, the smaller the wavelength, the smaller the distance between two consecutive loud sounds. Okay, so obviously my handwriting is all over the place, but yeah, I hope you get the idea lah. Okay, right. So the distance between two speakers is 0.8 meters as shown just now, and this one we know is A. If the boy walks a distance of 3.2 meters, this is D. Now he hears 5 consecutive loud sounds at a distance of 3.3 meters. Okay, let's visualize this properly. See, it's loud, 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 loud. Okay, loud, 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 loud. So there are 5 consecutive loud sounds, and the whole thing is 3.3 meters. Now remember that your X, okay, from the formula lambda equals to AX over D, the X is this distance. Okay, and so you need to look at it in terms of how many sets of loud sounds there are. So it's 1, 2, 3, 4. Okay, so there are 4 sets of loud sounds which equals to 3.3 meters. So one set will be 3.3 divided by 4, which will give you about 0.825 meters. Then you can substitute it in. So lambda equals to 0.8 times 0.825 over 3.2. Okay, be very careful about this. This is very common lah. Okay, they will give you 5 consecutive loud sounds and with the hopes that you will divide by 5, but actually you're dividing by 4. Okay, so 0.8 times 0.825 divided by 3.2 will give you about 0.206 meters. Okay, which sounds about correct. Okay, and then of course, you cannot run away from a question that will ask you from the wave equation. The speed of the sound waves or the velocity of the sound wave is given by the wave equation V equals to F lambda. So you have the frequency, which is given actually in the question much earlier, 600 hertz. Okay, so this will be 600 times the wavelength is 0.206. Okay, so this will give you about 123.75 wavelength meters per second. Okay, so this will be how. So interference is usually one of the questions where it kind of pao ka liao la, especially if it is in the back question. Sure, they will ask you to explain. Sure, they will ask you to use the formula. The formula, again, as I said, is pretty easy to remember if you can visualize it. Okay, visualize, okay, this is the A, this is the X, this is the D. Rather than, oh, A is the distance between, and then X is the distance between, and then D is the distance between, blah, blah, blah. It's very long and very long-winded, and you don't really have to memorize it if you know where it is positioned. Okay, because interference cannot run far. Just replace the loudspeakers with 2 light sources, replace the loudspeaker with 2, dipper for the, for the water waves, okay, ripple tanks. Same thing. Okay, same thing. All right, let's go to the next question. Okay, so now we are in this question 5. Okay, and so I need to pause here for a while and remind you the question 5 and question 6 are what we are estimating to be the compare. Okay, compare and relate question. The one that says the bigger the this, the bigger the that. Okay, that's the relating question. So we need to have this in mind. 5 and 6, we are going to assume that this is what's going to happen in SPM, because last year it happened in SPM. Okay, hopefully this year won't be that much of a difference now. Okay, now diagram 5.1 and 5.2 show 2 toy cars that are remotely controlled using radio wave from respective controllers. So if we take a look at the controller, this is 2.7 times 10 to the power 7 hertz, but as the second one is 4.9 times 10 to the power 7 hertz. The distance is 60 meters over here and 90 meters over here. Okay, so this is a remote control car, obviously using radio waves. Okay, so F is the frequency, and then X, okay, this distance is the maximum distance that can emitted by the transmitter that can be detected by the antenna. Okay, so when you look at this, you kind of obviously know that, oh, okay, there's a relationship here that needs to be mentioned lah. So underline the correct answer. The speed of the radio wave is smaller than, equals to, bigger than the speed of light. Okay, the answer is equals to, because okay, radio wave is part of the electromagnetic waves, electromagnetic spectrum, and every wave in the electromagnetic spectrum travels at the speed of light. Do not equate radio waves to sound waves. Sound wave is smaller than the speed of light. But radio wave is not a sound wave. Radio wave is an electromagnetic waves. And all electromagnetic waves, okay, which if you remember the guest experience unique, blah, blah, blah in my room, okay, all those travel at the speed of light, which is 3 times 10 to the power 8 meters per second. Okay, so this question looks very deceptive, okay, but you need to remember radio waves and sound waves are 2 totally different waves altogether, and they don't travel at the same speed. Compare the frequency of the radio wave emitted by the transmitter of controller A and B. One look and you know lah, okay, A is smaller than B, okay, the frequency, because the 2.7 is smaller than 4.9. Okay, next, tick for the correct answer. Okay, toy car A still can be controlled even though its distance is 80 meters. Obviously cannot lah, because the maximum is to be 60 meters. So the answer will be B. Okay, B can be controlled even though it is 80 meters, because it can hold up all the way to 90. So calculate the wavelength if the of the radio wave emitted by the transmitter of controller A and B. So once again, if you want to calculate the wavelength, you need to remember that we are using the wave equation. So over here is V equals to F lambda. Of course, our V, okay, is because it's radio wave, so it travels at speed of light. So 3 times 10 to the power 8 equals to, so for controller A is 2.7 times 10 to the power 7. 2.7 times 10 to the power 7, then you get lambda. You calculate lambda by dividing 3 and 2.7. So 3 to the power 8 divided by 2.7 to the power 7. You get about 11.11 meters. Okay, do the same thing for the second controller. Second controller is 4.9 times 10 to the power 7. Okay, so 3 to the power 8 divided by 4.9 times 10 to the power 7. You'll get about 6.12 meters. Okay, which verifies what I've been saying just now, that the bigger the frequency, the smaller the wavelength. So based on the answer in 5C, state the difference, okay, between the wavelength of the radio wave emitted by controller A and controller B. Okay, so if you look at this one, look at the wavelength. Now, I'm a little bit divided on this question, okay? I'm a little bit conflicted, because I know that this is a compare question, okay? And they are saying that this is a difference question. So I guess they could accept either one of these answers. If you say a difference, so the difference, okay, would be 11.11 minus 6.12, which is a difference of 4.99 meters. Which is a little bit odd, because why would they? It's a little bit odd that they will ask you to count the difference, but you know, it's kind of like apa tujuannya lah, like what's the point of counting the difference? So I would feel, based on what I know on question 5, I think they're asking you to compare, okay, the wavelength between controller A and controller B, which is obviously the wavelength of controller A is bigger than the wavelength of controller B. I would say that this is a more better answer for this kind of question. Okay, but the word difference, bila kita nyatakan perbezaan kan, we think about it mathematically, say, oh, okay, you want a minus. Okay, so if you ask me, I think the one that I take red in this one is the better answer. I think if you give a numerical answer, could be accepted also, I guess. Okay, then now we come to the relationship question. We relate the frequency and the maximum distance of the radio wave. So obviously, the bigger the frequency, the bigger the, the bigger the frequency, the bigger the maximum distance lah. Okay, of course, I encourage you to write this in full sentence or however you write it lah. Okay, again, reminding you, do not use the words directly or inversely proportional, simply because there's no graph over here. Okay, this is a situation that is not plotted in a graph. So don't use the words directly proportional, especially in paper 2. Okay, next, state the relationship between frequency and the wavelength. Okay, this one can go both ways. Either the bigger the frequency, the smaller the wavelength, or the bigger the smaller the bigger the wavelength, the smaller the frequency. Okay, in this case, the order is not so important, but in the first case, the order is very important. The frequency affects the maximum distance. You cannot terbalik this round. You cannot say, oh, the bigger the maximum distance, the bigger the frequency. Salah. Okay, because the order is very important. Okay. All right. Let's continue on to question number 5. So this is a question that involves mirror, etc., etc. Concave mirrors specifically. So whenever we talk about mirror, obviously the light phenomena that is involved is reflection lah. Okay, just to remind you, the refraction is lens. Okay, but for mirror it's reflection. So based on diagram 1, 5.1, 5.2, compare the object distance. Obviously 5.1 is 5.1 is nearer lah. Okay, than 5.2 object. So 5.1 is smaller than 5.2. Okay, lebih dekat lah. Okay, compared to 5.2. Compare the image distance. 5.1 is much further than 5.2. So 5.1 is bigger than 5.2. Compare the size of the image. If we take a look, the image in 5.1 compared to the one in 5.2 is much bigger. So 5.1 is bigger than 5.2. So after you do the comparing, obviously you have to relate lah. So relate the object distance with the image distance. Since the object distance and the image distance have different directions, okay, so it'll be the bigger lah, the bigger the smaller. So the bigger the object distance, okay, the bigger the object distance, the smaller the image distance. Okay, this is pretty standard lah. Okay, then of course relate the object distance with the size of the image. So you take the object distance, the nearer one has a bigger image. Okay, so the bigger the object distance, or the other way around also if you want. Okay, I'm going to write smaller now. Smaller the object distance, the bigger the size of image. Okay, or the other way around. Okay, it doesn't either one is fine lah. But the idea is that they are not directly proportional. Okay, showing an incomplete array diagram. Complete the array diagram to show. So remember that all light rays have to reflect back to F. Okay, so the first line will be after it comes here, then it will reflect back to F like this. Okay, make sure to draw the anak panah. Let me put it a bit bigger lah, so easier to see. Okay, then the second one will be straight through C. Oh, sorry. Okay, actually it should be going through C and coming back here lah. But because they're not meeting over here, so we have to extend. Okay, extend it further at the back because obviously this will be a virtual image. So this one when you extend, okay, so you will meet somewhere here lah. Okay, something like this. Okay, so show how the image is formed. So the first mark will be for the blue color ray, the one that goes to the mirror and then is reflected back to the focal point. The second one is the one that goes to the mirror and reflected back on the same line as the center of the curvature. And then after that, the third mark is for joining the two dotted lines together with drawing the image, okay, of the object lah. Okay, that will be the third mark. So that's how we would answer this question. All right, next, another one. Diagram 5.1, 5.2 show a hotel porter, etc., etc. There's a net force. Okay, taking into account, looking at this, all right, causing it to accelerate from P to Q. So the position of P to Q is different, but with the same time interval. Okay, this is a very interesting. Okay, so I think this gambar one is a little bit weird lah. Okay, but basically this is the distance of P and Q. This is the distance of P and Q. Yeah, but it is the same amount of time. Okay, so the time is the same from P to Q. Okay, I don't really understand the first picture, but anyway, what is the meaning of frictional force? It is a force that opposes motion on a surface. All right. Now compare the mass of the loaded trolley. You can look at 5.1, 5.2. So obviously 5.1 is less than 5.2. Okay, that's quite easy to see lah. 1 bag, 3 bags. Okay, so second one is compare the force on the hotel porter that is exerted on the trolley. I think it looks like it is the same lah, because although it's not really mentioned over here, but since everything is changing, one of it has to be the same lah. Okay, so the force, okay, is equal. Okay, so when you compare the acceleration on the trolley, obviously acceleration of 5.1 will be higher lah. Okay, or 5.2 is smaller, whichever one that you want lah. So 5.1 is bigger than 5.2. Okay, the acceleration. Okay, then say the relationship between the mass and the acceleration. So the bigger the mass, the smaller the acceleration. Again, I'm just writing this in symbols for us to this one, but I'm not really, of course, you should write it in more proper sentences lah. Okay, the law involved here is Newton's second, okay, law of motion. Okay, or Newton's second law is fine. You don't have to say of motion. Okay, what happens to the acceleration of the trolley if the hotel porter push the trolley with only one hand? using only one hand. Okay, let's assume now that every hand plays a role in the force lah. Okay, so obviously the acceleration will decrease lah. Okay, will decrease. Okay, so why will the acceleration decrease? Because the force is the force is lessened. Okay, so that's one mark. And then of course you have to say that the acceleration, okay, is well, I guess you can say directly proportional, okay, to the force, which is Newton's second law lah. Okay, so it's a very funny question lah. Wonder whether two hands or one hand really makes such a big difference. But yeah, anyway, let's just assume that every hand has a force to play in this lah. Okay. All right, the next question. 5.1 shows the soup that is boiling in a metal pot and in a clay pot. Both pots and soups are supplied with the same rate of heat and have the same mass. So a lot of same things here. Diagram 5.2 shows the changes in temperature after 5 minutes. Okay, you can clearly see what's happening over here. So, question, what is meant by specific heat capacity? Okay, so here we go. The heat required. Okay, remember, the unit for specific heat capacity is joule per kilogram per degree Celsius. So all the units need to be in. So the heat required to raise the temperature of 1 kg object by 1 degree Celsius. Okay, is specific heat capacity. Heat required to raise the temperature of 1 kg object by 1 degree Celsius. Okay, compare the temperature of the soup in the metal pot and the soup in the clay pot after 5 minutes. So obviously after 5 minutes, the metal pot is higher lah. Okay, so metal pot temperature. Okay, metal pot is bigger than clay pot. Okay, compare the specific heat capacity of the metal pot. Is the values given? No, the value is not given, but you should know this lah. Okay, for metal and clay, sebab dia cepat panas, maka cepat panas means the specific heat capacity is smaller, okay, than the clay pot. Compare the mass of the soup. This is actually given in the question. Okay, the soups and pots, everything all have the same rate of heat and the same mass, so they are equal. Okay, and you compare the initial temperature. If you take a look, both the initial temperatures are the same. Okay, so we also say equal. All right, and so we state the relationship between the change in temperature and the specific heat capacity. Now, this is a very important thing. Notice that the question say change in temperature first, then specific heat capacity. But if you think about it, the change in temperature is the effect. The specific heat capacity is the one that affects the change in temperature. So specific heat capacity must come first. Okay, so the bigger the specific heat capacity, okay, the smaller the change in temperature, which means that takes a longer time to get hot or takes a longer time to get cold. It works both ways. Okay, takes a longer time to get hot, takes a longer time to get cold. Okay, specific capacity of water is etc. etc. Mass of water is this one. Initial temperature is 32. Calculate the heat needed to boil the meat in the water until it reaches boiling point. Okay, I really don't know what we are counting. Are we counting the boiling point of meat or are we counting the boiling point of water? But if I look at the Malay, kirakan haba yang diperlukan untuk mendidihkan daging bersama air sehingga tak didih lah. So I guess we're counting the boiling point of water lah. Okay, which is 100 degrees Celsius. So Q equals to MC delta theta. M is 0.8, C is 4,200, and C is theta is 100 minus 32. We want it to go up by 68 degrees. Okay, so 100 minus 32 is 68 degrees times 4200 times 0.8 will give you about 228480 joules. Okay. All right, next. Wow, there's a lot of comparing questions. Okay, diagram 5.1a shows the phenomenon of light on mirror P. Okay, another mirror question. Okay, Cx is the radius of curvature and F is the focus point. Okay, what is the meaning of focal point? So focal point is a point where all the light converges lah. Okay, so the point in which the light converges. Of course, this is mirror, so this would be after reflection. Okay. Next, compare the curvature of the mirrors. If we take a look at the curvature should be the same. Okay, Cx is the radius of the curvature. Oh no, sorry. The curvature of Cx over here. So 5.1b is bigger than 5.1a. Okay, compare the focal length. This is the focal length, sorry. This is the focal length in red, and this is the focal length in red over here. So we have the same answer lah. 5.1b is bigger than 5.1a. Okay, the effect of the angle of reflection. What is the effect? Kesan ke atas sinar cahaya yang dipantulan. Okay. Well, I guess the angle in 5.1a is bigger than angle 5.1b. Okay. It's a slightly strange question, but definitely this angle is bigger than this angle. Okay, we take a look at it. So state the relationship between the curvature and the focal length. So obviously, the bigger the curvature, okay, the bigger the focal length. Okay, that one is quite obvious over here. Next, draw, okay, so again, drawing the same thing. So draw a ray to perform an image, not perform now, to form, okay, an image for the mirror. Since this is a convex mirror, you know that it will diverge lah. So the first line will be from the object over here. And then of course you will have to, this one first, and then it will reflect this way. Okay, and then of course the second one is directly from the head over here all the way to the C, which would be like this. Oh no, sorry. Okay, something like this lah. Okay, but actually here should be dotted lines, but okay, doesn't matter. But anyway, the meeting point of this is where the image is. Okay, so as always, 1 mark for the first reflected ray, the second mark for the second reflected ray. Sorry, this one should be here, and then this one will go back. Okay, and then of course the third mark will be for the drawing of the image itself. Okay, let's continue with the next question. So you have these two diagrams showing the phenomenon of refraction, okay, as shown over here. So what is the meaning of refraction? So I guess the most important one is the refraction is the bending. Of course, if we are talking about light, as in this case, so we say the bending of light waves lah. Okay, so bending of light waves. But there's a condition to this. As it passes through THROUGH mediums with different densities. Okay, that's one definition of refraction. I think there are several. Okay, one has to do with the changing wave speed because of the different density of the medium that they're traveling in. So that is also possible lah. Okay, so give one reason why the lights undergo bending after propagating in different medias, because the wave speeds change. Okay, or the wave speeds decrease. Is it decrease? Sorry, wait, air to diamond, air to glass, correct? Air to, yeah, so the wave speeds change or the wave speeds decrease as they enter the different medium. Okay, or you can say that the density of the mediums are different that causes this one lah. But the reason why the wave actually bends is because as it enters into the different density, okay, the wave speed will reduce, or well, the wave speed will change lah. So therefore, they also have to change their propagation, okay, whether it is away from normal or towards the normal lah. Okay, C, compare, okay, so we're going to compare the angle of refraction, the refractive index, and the optical density. So angle of refraction, 32 and 21, so obviously 5.1 is bigger than 5.2. Okay, the refractive index, since this one is 2.42 and this one is 1.63, obviously 5.2 is bigger than 5.1. Okay, and then of course, optical density usually has to do with the refractive index, and it follows the more dense the material is, the bigger the optical density. So 5.2 is more than 5.1. And even if you don't know, actually you can see that glass and diamond, because diamond is more dense, optically dense, okay, it is able to refract light more. Okay, that's the meaning. Something that is optically dense can refract light more, and therefore it will bend much nearer to the normal. Okay, so because of that, let's state the relationship between angle of refraction and refractive index. So obviously, the bigger the refractive index, the smaller the angle of refraction. Okay, as shown over here. And again, the order is very important. Refractive index is the one that determines the angle of refraction, not the other way around. Okay, secondly, the refractive index and the optical density. So the good news is, I would feel that it can be either way, but if it were up to me, I would say the bigger the optical density, the bigger the optical density, the bigger the refractive index. Okay, or all right, next, if the angle of incidence is 70, calculate the angle of refraction. Okay, so this formula is n equals to sine I over sine R. So your density, 5.2, or the angle is 70. So an n in 5.2 is given as 2.42. Okay, so you have 2.42 equals to sine 70 over sine R. Of course, you want to find R lah. Okay, so sine R will be sine 70, the whole thing divided by 2.42. When you press the calculator, be careful not to make this mistake. Calculate sine 70 first, then only you divide by 2.42. Okay, then after that you shift sine, and you will get R is equals to about 22.85 degrees. Okay, something like that lah. Quite a simple question. I don't think there's not anything really very challenging here, except that just remember this one, I noticed that a lot of students tend to make the calculation here a bit complicated because they don't know how to press on the calculator. Okay, so be careful with that. All right, let's go to the question number 6, which is the final question for this video. Okay, it's a pretty long video. Okay, so what is pressure? Okay, pressure is force, per unit area. Okay, this is the standard definition for pressure. Okay, then question B. So based on diagram 6.1a, compare the horizontal distance. So if you take a look at the horizontal distance and how far this is, obviously 6.1b is much bigger lah. Okay, so 6.1b is bigger than 6.1a. The depth of the hole, 25 centimeters and 40 centimeters. Once again, 6.1b is bigger than 6.1a. And just to remind you that the depth is counted from the surface and not from the bottom. Okay, so especially because this tends to be a common mistake lah. Okay, the depth is always counted from the surface and not from the bottom. All right, next, the real depth of the container. Okay, the real depth of the container, both is 50 cm. Okay, so it is equal. And the density of the water, well, I guess that the density is the same. Okay, because both are filled with water. Okay, so it's also equal. So then the relationship between the depth and pressure obviously is the bigger the depth, okay, the bigger the pressure, which is represented by the horizontal distance of the water coming out. Okay, so the water is replaced with a high density liquid. So the question is, what will happen to the horizontal distance? I noticed that sometimes what will happen questions tend to be very focused on, or tend to be very based on formulas. So for example, a liquid pressure is P equals to rho GH. So when you increase the density, okay, you will also increase the pressure. So the horizontal distance will also increase. So state the two factors that affect the pressure in liquid. Of course, it will be the depth, okay, of liquid, and of course, the density of liquid. Actually, technically, there's a third one, which is the gravitational acceleration. But I guess since we're talking about on Earth, so gravitational acceleration is kind of a constant. So you don't really put gravitational acceleration into this picture. Okay. But I have to comment though about this question. This question is a little bit out of how to say, not very standard okay, because number one, they ask two things to compare, and then they give you two things to compare that are equal, which is very rare. Okay, it's very rare to get two things that are equal, and you're kind of wondering what is the point of these two things Okay, and then of course, there is a repeat Okay, because you're already talking about the density liquid, and then you still have to give the answer the density of the liquid. So it's a little bit not very standard. Okay, but I guess for practice purposes, it's quite okay. All right, let's move to the next question. Diagram 6.1 shows two identical bottles, P and Q, filled with sand, floating stationary in the water. Okay, so you notice that P is higher than Q. Okay, more this one. This is probably Archimedes' principle. Okay, so bottle Q floats stationary because obviously the forces are equal. Okay, the weight is equal to the buoyant force. Okay, which is why it floats stationary in water. Now compare the weight of both the bottles P and Q. I think it's quite safe to say that Q is heavier, okay, heavier than P. So the weight of Q is bigger than the weight of P. Oh, sorry. Okay, the weight of P. Now compare the volume of bottles P and Q that are immersed. So we notice that Q is more immersed, okay, in the water. So once again, Q is bigger immersion than P. So compare the weight of the water displaced by bottles P and Q. Once again, Q is bigger than P. Okay, so state the relationship between the weight of the water displaced and the volume of the bottle immersed. Okay, so is the bigger the volume of the bottle immersed, not the bigger the volume. Okay, the bigger the volume that is immersed in the water, the bigger the weight of the water displaced. Again, the volume is the one that displaces the water. Okay, the bottle goes inside the water, then the water gets displaced. So the cause is the volume and the effect is in the weight. Okay, the relationship between the weight of the water displaced and the weight of the bottle is actually equal. Okay, this is a very interesting thing okay, because we established the fact that the weight of the bottle is the same as the buoyant force. And since the weight of the bottle is the same as the buoyant force in this situation, okay, since it's floating, okay, so the weight of the bottle is actually equal. Okay, and we find out that usually in Archimedes principle questions, okay, this is usually the case. Okay, and so it's a very interesting relationship because it is the Archimedes principle relationship. Okay, the weight of the bottle that is in the water, for floating objects, the weight of the bottle is equal to the weight of the water displaced. Okay, so weight of bottle is equal to weight of water displaced. Again, with the prerequisite that it is floating stationary. Okay, if it is bobbing up and down, it's a totally different story altogether. Okay, so the next one is diagram 6.2 shows a boat with two passengers, okay, and the loads moving from the sea to the river. Okay, so sea to the river usually refers to different densities okay, so we need to be very careful of this. And so the question is, what the immersed level of boat increases as it moves towards the river. Okay, what should be done to make sure that the boat will not sink. Okay, so you obviously need to reduce the weight of the boat lah. Okay, so you can reduce the weight of the boat, okay, by putting away the load, because as you can see, there are all these loads that, I mean, you can't do the I guess you can throw away the passengers if you want lah. Of course, naturally the load is the more important one lah. Okay, so reduce by removing the loads. Okay, and why do we do this? Give one reason is, okay, so to reduce, okay, and either one of these answers is fine, to reduce the volume of water displaced, therefore reducing the buoyant force, or okay, to reduce the weight of water displaced. Okay, so why do we throw away throw away the load so that we can reduce the weight of the water displaced? Because as you move from sea to river water, okay, which is here, okay, as you move from sea to river water, the density will decrease. Okay, and the formula for the buoyant force is F equals to rho GV. Okay, F equals to rho GV, because the density is now decreasing. Seawater is generally, more dense okay, than river water. So since the since the density is decreasing, okay, we are going to assume that the buoyant force also will decrease. Okay, and so if the buoyant force is going to decrease, the ship has a likelihood of sinking lah. Okay, so one way to this one is to throw away the load. Okay, that's very natural. Throw away the load. Okay, so that there will be less water displaced. Okay, and so you are able to stay afloat lah. Okay, to make up, to kind of balance out that reduction of the density. Okay, so the law involved here, okay, this is very important lah. This is not actually Archimedes' principle, but we're actually referring to the flotation law, or the law of flotation, sorry. Okay, law of flotation, where you want to balance out everything. The weight has to be equal to the buoyant force, okay, in order for it not to be sinking. So as you move from the sea to the river, the buoyant force is reducing. So you have to reduce your weight so that you will continue to keep afloat. Okay, very important. I think the most difficult part about Archimedes' principle, at least in my experience, the most difficult part is usually differentiating between the law of flotation and Archimedes' principle. Archimedes' principle is basically, or if you want more buoyant force, then you have to increase the weight of water displaced. But now, we're not talking about the force that pushes the thing up or pushes the thing down. The ship is already floating. Of course, it's floating on the sea. Okay, and in order to keep it afloat, okay, the buoyant force must be equal to the weight of the ship lah. Okay, and since it is going from sea to river, okay, the buoyant force is going to decrease because obviously the volume is not increasing yet lah. Okay, but the density is decreasing. That's why the buoyant force is decreasing. And so if the buoyant force is decreasing, you're going to have a situation where the weight is going to be bigger than the buoyant force when it is going into the river water. And so in order to counter that, you have to reduce the weight so that it goes back into its original flotation mode. Okay, because like it or not, it's going to decrease. Okay, you cannot change the volume, you cannot change the volume of the distance because it's the size of the ship, okay, and you cannot change the gravitational acceleration. The only thing that changes is the density. So the only way to do it is to counter it with the reduction of weight on the ship. Okay, so yes, it is quite a tough thing to grasp because it's two concepts and they are like as if they are in opposition, but actually they're not lah. Okay, we just have to know when to use Archimedes principle and when to use law of flotation. All right. Is this the last question? No, it's not. There's still a couple more questions. Okay. Okay, diagram 6.1 shows a boy, which is Homer Simpson, strangely enough, playing a skateboard game which moves with constant speed. Okay, so this one is constant speed. Number 2 is playing a skateboard with increasing speed, that means it's accelerating as it pushes its leg harder and faster. Oh, wow. Okay, so what is the resultant force? Okay, is the sum of all the forces acting on an object. Okay, that's the resultant force. So contrast the type of motion in a word of acceleration. So I like this question because they tell you to talk about the acceleration by compare it. So 6.1, there's no acceleration because it's constant speed, and 6.2, there is acceleration. Okay, so 6.1, no acceleration. Okay, 6.2, the boy moves with an acceleration. Okay, so the resultant force that acts on the boy, okay, so in this case, 6.1, the resultant force is 0 because the forward and the backward is the same. But in 6.2, the forward thrust is bigger than the air resistance. So the resultant force will be more than 0 lah. So I think there's two ways to answer this question. My preferred way would be there is no, oh sorry, 0 lah, resultant force in diagram 6.1, and there is a resultant force which we don't know how much lah. Okay, there is a resultant force in diagram 6.2. But I guess if you want to say, if you really want to go back to the principle of comparing, which is, this is more than that. So obviously it'd be 6.2 is more than 6.1 lah, because 6.2 has a resultant force and 6.1 doesn't have. Okay, but honestly, I feel that this is my preferred way of answering, at least for me. Okay. Now the forward thrust with the air resistance, you're comparing the forward thrust with the air resistance on diagram 6.1 and 6.2. Okay, so and this is a very strange question. So we don't know whether we're supposed to compare the forward thrust in 6.1, 6.2 and then the air resistance 6.1, 6.2. But since it says forward thrust with air resistance, okay, again, I think this is a wording problem, wording issue. If you're not sure, write as much as you can. I know it's only 1 mark, but don't be satisfied with the one answer. Okay, so yeah, it happens sometimes. Even in exam, we find that the question is worded so strangely, So we don't know, are we supposed to compare 6.1, 6.2? Are we supposed to talk about, the forward thrust and the air resistance in both 6.1 and 6.2? So if you don't know and if you're not sure, even though it's only 1 mark, overwrite. Okay, just write a lot more, but make sure that whatever you write is not, bercanggahan, it's not contrasting. So if I were to overwrite this, okay, I would say that, okay, forward, okay, if I would say forward thrust okay, 6.1 is less than 6.2. Okay, definitely 6.1 is less than 6.2. In terms of the air resistance, okay, air resistance in both situations is actually equal. Because the same person is the same Homer Simpson as facing against the air. So the air resistance is definitely equal. Okay, again, this is a strange question for just 1 mark. I'm not actually sure what they're trying to compare. Are we supposed to compare the forward thrust with air resistance or 6.1 and 6.2? Okay, but there is another way to answer this, which is in 6.1, okay, the forward thrust, okay, is equal to the air resistance. But in 6.2, the forward thrust is more than the air resistance, which is why there's an acceleration. Okay, so this is what I mean by overwriting, because I don't know actually what the question wants. Honestly, if you ask me, I think the way the question is worded is very ambiguous. Like, saya tidak tahu sebenarnya apa yang soalan ini mau. Dia mau saya compare 6.1, 6.2, or do you want me to compare forward thrust and air resistance in 6.1, 6.2, or in 6.1 done separately in 6.2? So well, if this happens in your exam, overwrite it. And it's not wrong because none of these four statements here are wrong. So you will not be penalized. Lain lah kalau kau tulis benda yang salah. But none of these four statements that I've just written over here, sorry, I'm pointing to my own tab, none of these four statements are false. So you definitely cannot be wrong. Okay, it's not your fault lah. Okay, but you will have to memang answer a little bit more extra lah. Okay, right, state the conclusion between the relationship between the type of motion with the resultant force. So obviously, when there is an acceleration, okay, there is a resultant force. Again, very, very strange question, but since it's type of motion, okay, so when there is an acceleration, there will be a resultant force, okay, or the resultant force is more than 0. Okay, either one of these. Okay, forward thrust with the resultant force. Okay, this one, state the relationship between the forward thrust and the resultant force. Okay, so don't know. If the forward thrust is bigger, then the resultant force is bigger lah. Okay, so the bigger the forward thrust, because that's what happens in 6.2, okay, the bigger the resultant force. Okay, so it's an interesting question now, but still pretty strange lah if you ask me. Okay, especially this one lah, I really don't know lah. Okay, oh, we are at the last one already. Okay, now if the mass of the boy and the skateboard is 60 kg and 2.8 kg respectively, accelerates at 3 meters per second squared, calculate the forward thrust. Okay, now assume the air resistance is 40 Newton. Again, I don't understand why they would give this line over here, but that's not our problem lah. Okay, your problem is to remember that the forward thrust minus the 14 is equals to the total weight, total mass, which is 60 plus 2.8. Okay, this is a very heavy skateboard, 2 kg. Wow, very heavy. Okay, times the acceleration of 3. Okay, and you will get F will be equals to 62.8 times 3 plus 40. Okay, it's about 202.4 newtons. Okay, that will be the forward thrust. Again, coming back to Newton's second law lah. Okay, the net force equals to mass times acceleration. Now, the state the change that would happen if the skateboard is replaced with another board with a mass of 5 kg. Okay, as it continues his motion at 6.2. Okay, let's assume now. Let's assume that the change that they're talking would happen would be the change in the forward thrust. Okay, or you can also say the change. Oh no, you know what? I don't think it's the change in the forward thrust. I think it's assuming that the forward thrust is the same because it says continues its motion. So I guess what we're talking about is the change in the acceleration. So you're having the same forward thrust, you have the same resultant force, okay, except that the weight, the mass of the skateboard has increased. So we know that according to Newton's second law, the relationship between mass and acceleration, F over m equals to a. The relationship between mass and acceleration is inversely proportional. So if you increase the mass, okay, the acceleration of the skateboard will reduce. Okay, or decrease, sorry. I usually use the word decrease. Okay, so I guess the question is not asking us to change the forward thrust. Forward thrust is the same, but now you just change the mass of the skateboard. So we change mass of the skateboard, acceleration will decrease. Okay, so that's it for the set of questions from number 4 to number 6. Okay, so in the next video, I will do one that is discussing 7 and 8. All right, take care, everyone.